Right now, as you read these words, an invisible ocean of matter is flowing through your body. Every second, billions of dark matter particles pass through every atom of your being without leaving the slightest trace. You can't see them. You can't feel them. No telescope on Earth has ever captured their image, and no detector has ever recorded their presence directly. Yet this phantom matter outweighs everything we can see in the universe by a factor of 5 to 1. For over a century, humanity has illuminated the cosmos through light. From Galileo's first telescopic observations to the James Webb Space Telescope's infrared revelations, we've mapped galaxies, measured stellar temperatures, and decoded the chemical composition of distant worlds, all through electromagnetic radiation. Light has been our cosmic messenger, carrying information across billions of years to paint pictures of creation itself. But dark matter refuses to participate in this ancient conversation. It neither emits, absorbs, nor scatters a single photon. This electromagnetic silence isn't a limitation of our instruments. It's a fundamental property of dark matter itself. While every visible star, planet, and grain of cosmic dust announces its presence through radiation, dark matter remains perpetually mute to the electromagnetic spectrum. We know it exists because of its gravitational fingerprints, the way galaxies spin too fast to hold together, how light from distant quasars bends around invisible gravitational lenses, and the precise pattern of cosmic microwave background radiation that reveals the universe's infant structure. Now, let us begin our journey into the electromagnetic void, where the universe's greatest mystery dwells in perpetual darkness. Chapter 1. Hidden Architecture. The universe you see is a lie. Not intentionally deceptive, but incomplete in the most staggering way imaginable. Every star that twinkles in the night sky, every galaxy captured by our most powerful telescopes, every nebula glowing with the fires of stellar birth represents less than 5% of all the matter that exists. The remaining 95% dwells in complete electromagnetic darkness, invisible to every form of light we know how to detect. This revelation didn't emerge from abstract theoretical speculation. It began with a simple observation that shattered our understanding of cosmic architecture. In 1933, Swiss astronomer Fritz Zwicky was studying the Coma Cluster, a massive collection of galaxies bound together by gravity, when he noticed something impossible. The galaxies within this cluster were moving far too quickly. According to Newton's laws of gravity, they should have escaped the cluster's gravitational embrace billions of years ago, scattering across the cosmos like marbles rolling off a tilted table. Zwicky calculated that the visible matter in the cluster provided only about 1/10 the gravitational force needed to keep these high-speed galaxies bound together. Either our understanding of gravity was fundamentally wrong, or the cluster contained 10 times more matter than we could see. He termed this invisible component dunkel materie, dark matter, coining a phrase that would haunt cosmology for the next century. For 40 years, Zwicky's discovery remained an astronomical curiosity, a puzzling footnote in cosmic accounting. Then Vera Rubin turned her attention to spiral galaxies, and dark matter's significance exploded across the entire universe. Rubin measured how fast stars orbit around galactic centers, expecting to find that outer stars move more slowly than inner ones, just as outer planets orbit the sun more slowly than inner ones. Instead, she discovered that stars maintain nearly constant orbital speeds regardless of their distance from the galactic center. This observation violated everything we understood about orbital mechanics. Imagine if Jupiter circled the sun at the same speed as Mercury. Our solar system would fly apart in cosmic chaos. Yet galaxy after galaxy displayed this impossible rotation pattern. Stars on the galactic rim were racing around their centers at speeds that should have flung them into intergalactic space eons ago. The only explanation was that each galaxy contained roughly 10 times more matter than we could see, distributed in a vast invisible halo that extended far beyond the visible disk. The cosmic implications began cascading through astronomy. If individual galaxies required dark matter to maintain their structure, then dark matter wasn't some exotic rare substance. It was the dominant form of matter in the universe. Large-scale surveys revealed that galaxy clusters, the largest gravitationally bound structures in the cosmos, were held together by dark matter scaffolds. The cosmic web itself, that vast network of filaments connecting galaxy clusters across billions of light years, owed its existence to dark matter's gravitational architecture. Gravitational lensing observations provided independent confirmation of dark matter's cosmic abundance. When light from distant galaxies passes near massive dark matter concentrations, space-time curves around this invisible mass, bending the light paths like a cosmic lens. The Hubble Space Telescope has captured hundreds of these gravitational lensing events, revealing dark matter's distribution with stunning precision. In some cases, the lensing reveals dark matter clumps that contain no visible matter whatsoever, pure concentrations of gravitating invisibility. The cosmic microwave background radiation, that ancient light released 380,000 years after the Big Bang, carries dark matter's fingerprints in its temperature fluctuations. The Planck satellite has measured these fluctuations with extraordinary precision, revealing that dark matter comprises 26.8% of the universe's total mass energy content. By comparison, ordinary matter, everything from hydrogen atoms to neutron stars, accounts for only 4.9%. The remaining 68.3% consists of dark energy, but that's another mystery entirely. This means that for every kilogram of ordinary matter in the universe, there are more than 5 kilograms of dark matter. In your local cosmic neighborhood, dark matter particles are streaming through space at hundreds of kilometers per second, passing through planets, stars, and your body without interacting electromagnetically. The density of dark matter in our solar system averages about 1 proton mass per cubic centimeter, seemingly sparse. But this invisible presence extends throughout all of space, creating a vast reservoir of gravitating matter. What makes dark matter as electromagnetic silence even more remarkable is how thoroughly ordinary matter proclaims its presence through radiation. Stars shine because nuclear fusion in their cores converts mass into electromagnetic energy. Planets reflect starlight, revealing their compositions through spectroscopic signatures. Interstellar gas glows when energized by stellar radiation or heat-sucked during gravitational collapse. Even black holes, the universe's most extreme objects, announce themselves through the brilliant accretion disks formed by matter spiraling toward their event horizons. Yet dark matter participates in none of this electromagnetic drama. It doesn't emit radiation when heated, doesn't absorb photons when light passes through it, and doesn't scatter electromagnetic waves when they encounter dark matter particles. This silence isn't temporary or partial. It's absolute across the entire electromagnetic spectrum, from radio waves spanning kilometers to gamma rays with wavelengths smaller than atomic nuclei. Consider what this electromagnetic neutrality means for cosmic evolution. While ordinary matter can lose energy through radiation and collapse into dense structures, dark matter maintains its kinetic energy indefinitely. This allows dark matter to form extended halos around galaxies, while ordinary matter condenses into stars and planets at galactic centers. The universe, as large as structures, galaxy clusters, and cosmic filaments, owe their existence to dark matter's inability to radiate energy away. The search for dark matter has become one of humanity's greatest scientific endeavors. Underground laboratories shield sensitive detectors from cosmic radiation, hoping to catch the rare interaction between a dark matter particle and an atomic nucleus. Particle accelerators attempt to create dark matter in high-energy collisions, searching for missing energy that might signal dark matter production. Space-based gamma-ray telescopes scan the cosmos for the radiation signatures of dark matter annihilation. Yet despite decades of increasingly sophisticated searches, dark matter maintains its electromagnetic exile. This extraordinary property, the complete absence of electromagnetic interaction represents one of the deepest puzzles in modern physics. It suggests that dark matter belongs to a hidden sector of particle physics, interacting with ordinary matter only through gravity. Understanding why requires us to examine the quantum mechanical foundations of electromagnetic interaction itself. But first, we must confront an even more fundamental question. What exactly is electromagnetic radiation? And why does ordinary matter interact with it so readily, while dark matter remains forever silent? Chapter 2. Electromagnetic Essence. To understand why dark matter doesn't emit light, we must first grasp what light actually is, and the answer is far stranger than the simple wave or particle your physics textbook described. Electromagnetic radiation represents the universe's most fundamental form of communication, a quantum field that permeates all of space and mediates one of nature's 4 fundamental forces. Every photon that has ever existed, from the cosmic microwave background to the gamma rays produced in stellar cores, emerges from the same underlying mechanism: the electromagnetic interaction between charged particles. Light begins with electric charge, the intrinsic property that gives certain particles the ability to create electromagnetic fields. When a charged particle accelerates, it disturbs the electromagnetic field around it, sending ripples through space at exactly 299,792,458 meters per second. These ripples are what we call electromagnetic radiation photons, carrying energy and information across the cosmos. The frequency of these ripples determines whether we perceive them as radio waves, microwaves, infrared radiation, visible light, ultraviolet rays, X-rays, or gamma rays. But here's where quantum mechanics reveals the deeper truth. Electromagnetic radiation isn't just a byproduct of charged particle acceleration. It's the physical manifestation of the electromagnetic force itself. Every electromagnetic interaction, from the force holding electrons in atomic orbits to the magnetic fields generated by spinning neutron stars, occurs through the exchange of virtual photons, quantum field fluctuations that mediate the force between charged particles. James Clerk Maxwell unified electricity and magnetism into electromagnetic theory in 1865, revealing that light is simply electromagnetic waves propagating through space. His equations predicted that accelerating charged particles would radiate electromagnetic energy, explaining why orbiting electrons should spiral into atomic nuclei while radiating away their kinetic energy. This classical prediction created a crisis that helped birth quantum mechanics, but the fundamental principle remained. Charged particles interact with electromagnetic fields, and this interaction can produce observable radiation. The quantum mechanical description deepened this understanding. In quantum field theory, the electromagnetic field is quantized into photons, particles of light that carry electromagnetic force between charged particles. When an electron transitions between atomic energy levels, it can emit or absorb a photon whose energy exactly equals the energy difference between those levels. This quantum process explains why atoms produce characteristic spectral lines, creating the fingerprints that allow us to identify elements across cosmic distances. Every form of electromagnetic radiation follows this same quantum mechanical foundation. Thermal radiation emerges when charged particles in hot objects vibrate with kinetic energy, emitting photons with frequencies determined by the object's temperature. Synchrotron radiation occurs when charged particles accelerate in magnetic fields, spiraling around field lines while radiating electromagnetic energy. Bremsstrahlung radiation results when charged particles decelerate rapidly, converting their kinetic energy into photons. The key insight is this: electromagnetic radiation requires charged particles. Only particles that carry electric charge can create, absorb, or scatter photons. This is why ordinary matter, composed of electrically charged protons and electrons, interacts so readily with electromagnetic fields. Protons carry positive charge, electrons carry negative charge, and their electromagnetic interactions produce the entire spectrum of light we observe throughout the universe. Consider how thoroughly electromagnetic interaction dominates ordinary matter's behavior. Chemical bonds form through electromagnetic forces between charged particles. The mechanical properties of solids emerge from electromagnetic repulsion between electron clouds. The warmth you feel from sunlight results from electromagnetic radiation, exciting the charged particles in your skin. Even the nuclear forces that bind protons and neutrons in atomic nuclei, while ultimately mediated by the strong force, depend on electromagnetic interactions to overcome the electrical repulsion between positively charged protons. This electromagnetic intimacy explains why ordinary matter announces its presence so dramatically throughout the cosmos. Stars shine because electromagnetic forces govern the nuclear fusion reactions in their cores, converting hydrogen into helium while releasing tremendous electromagnetic energy. Planetary atmospheres glow when stellar radiation excites their charged particles. Interstellar gas clouds radiate when gravitational collapse heats their constituent atoms, causing electrons to transition between energy levels while emitting characteristic photons. The universe's electromagnetic visibility extends across an enormous range of energies and distances. Radio waves from rotating neutron stars can travel billions of light years while maintaining enough coherence to reveal the precise timing of pulsar rotation. Visible light from distant galaxies carries information about their chemical composition, temperature, and motion through space. X-ray emission from matter falling into black holes reveals the extreme physics of spacetime near event horizons. Gamma rays from cosmic ray interactions probe the highest energy processes in the universe. Yet this electromagnetic abundance depends entirely on the presence of electrically charged particles. Every photon in the cosmic electromagnetic spectrum owes its existence to the acceleration, deceleration, or energy state transitions of charged particles. Remove the electric charge from matter, and the entire electromagnetic universe disappears into silence. This reveals the crucial question about dark matter. Does it carry electric charge? If dark matter particles possess electric charge like protons and electrons, they should interact electromagnetically and produce observable radiation. If they lack electric charge entirely, they would remain electromagnetically invisible regardless of their abundance or behavior. The overwhelming observational evidence points toward the latter possibility. Dark matter appears to be electromagnetically neutral. But electromagnetic neutrality alone doesn't fully explain dark matter's behavior. After all, neutrons are electrically neutral, yet they still interact with electromagnetic fields through their magnetic moments and can scatter photons through various quantum processes. Dark matter's electromagnetic silence appears more complete than simple charge neutrality would predict. The mystery deepens when we consider that even electrically neutral particles in the standard model of particle physics can interact electromagnetically through indirect mechanisms. Neutrons, despite having no net electric charge, contain charged quarks and can interact with photons through their internal electromagnetic structure. Neutrinos, nearly massless particles that rarely interact with matter, can still scatter off electrons through weak force interactions that involve electromagnetic components. Yet dark matter appears immune to even these indirect electromagnetic interactions. It passes through electromagnetic fields without deflection, travels through dense regions of ordinary matter without absorption or scattering, and maintains its kinetic energy indefinitely without radiating electromagnetic energy. This suggests that dark matter's relationship with the electromagnetic force is fundamentally different from any particle we know in the standard model. The implications of this electromagnetic exile are profound for cosmic structure formation. While ordinary matter can lose energy through electromagnetic radiation and collapse into dense structures like stars and planets, dark matter maintains its gravitational influence while remaining diffusely distributed. This allows dark matter to form the extended halos that provide gravitational scaffolds for galaxy formation while avoiding the electromagnetic cooling that would cause it to condense into compact objects. Understanding dark matter's electromagnetic silence requires us to explore the quantum mechanical foundations of particle interactions themselves. Why do some particles carry electric charge while others remain neutral? How do the fundamental forces of nature determine which particles can interact electromagnetically? And what does dark matter's electromagnetic immunity reveal about the hidden architecture of physical reality? These questions lead us to examine the standard model of particle physics and the possibility that dark matter belongs to an entirely separate sector of particles, a hidden realm that interacts with our electromagnetic universe only through gravity's cosmic embrace. Chapter 3. Particle Foundations. Deep within every atom lies a universe of quantum interactions so precise and fundamental that they determine whether matter can ever touch light. The standard model of particle physics, humanity's most successful theoretical framework, describes how particles acquire mass, charge, and the ability to interact with fundamental forces. Yet this elegant theory, validated by countless experiments and capable of predicting particle interactions to extraordinary precision, has one glaring omission. It contains no viable candidates for dark matter. The standard model organizes matter into 12 fundamental fermions, the building blocks of everything visible in the universe. 6 of these are quarks: up, down, charm, strange, top, and bottom. These combine in groups of 3 to form protons and neutrons, or in pairs to create exotic mesons. The remaining 6 are leptons, the electron, muon, and tau particles, each paired with its corresponding neutrino. Every form of ordinary matter, from hydrogen atoms to neutron stars, consists of these 12 fundamental particles held together by 4 forces mediated by gauge bosons. What makes these particles electromagnetically active is a quantum property called electric charge, measured in units of the elementary charge carried by a proton. Up quarks carry plus 2/3 charge, down quarks carry minus 1/3 charge, and electrons carry minus 1 charge. When quarks combine to form protons, 2 up quarks plus 1 down quark, their charges sum to plus 1. Neutrons, 1 up quark plus 2 down quarks, achieve charge neutrality. Yet, they still contain charged constituents that can interact electromagnetically. This internal structure explains why even electrically neutral particles in the standard model can interact with electromagnetic fields. Neutrons possess magnetic moments because their constituent quarks carry both charge and quantum spin. They can absorb or scatter photons through processes involving their internal electromagnetic structure. Neutral atoms can polarize in electric fields because their electrons can shift relative to their nuclei. Even neutrinos, which interact only through the weak nuclear force, can scatter off electrons in processes that involve virtual photon exchange. The standard model's electromagnetic interactions arise through quantum field theory, where forces manifest as exchanges of virtual particles. The electromagnetic force is mediated by photons, massless particles that can carry electromagnetic influence across infinite distances at the speed of light. Any particle that carries electric charge couples to the electromagnetic field and can emit, absorb, or exchange virtual photons. The strength of this coupling is determined by the fine structure constant, approximately 137th, which governs the intensity of electromagnetic interactions throughout the universe. But here is what makes dark matter so puzzling. If it consisted of any known standard model particle, we should have detected it by now. Quarks are confined within hadrons and would produce characteristic electromagnetic signatures. Electrons would ionize surrounding matter and create detectable radiation. Even neutrinos, despite their weak interactions, can be detected by massive underground observatories that capture the rare occasions when neutrinos interact with atomic nuclei. The most neutrino-like standard model particles are the three known neutrino types, but these cannot account for dark matter's observed properties. Neutrinos have tiny masses and travel at nearly the speed of light, making them hot dark matter that would erase small-scale cosmic structure through free streaming. Observations of galaxy formation require cold, dark matter particles massive enough to move slowly and form gravitational clumps on scales from dwarf galaxies to galaxy clusters. Moreover, even if neutrinos had the right mass and velocity, their weak force interactions would make them detectable in current experiments. The fact that we can detect neutrinos from the sun, nuclear reactors, and cosmic ray interactions proves that even weakly interacting particles leave observable signatures when present in sufficient abundance. Dark matter's complete observational absence suggests interactions far weaker than even neutrinos possess. This observational void has led theoretical physicists to propose that dark matter belongs to a hidden sector of particle physics, a realm of particles that exist beyond the standard model and interact with ordinary matter primarily through gravity. These hypothetical particles would lack electric charge entirely, making them invisible to electromagnetic radiation. They might possess their own hidden forces that govern their internal interactions while remaining hidden from our electromagnetic universe. The most popular dark matter candidate is the weakly interacting massive particle, or WIMP. These hypothetical particles would possess masses comparable to atomic nuclei but interact with ordinary matter only through gravity and possibly the weak nuclear force. WIMPs could have been produced in the early universe through thermal processes, then frozen out when the universe cooled below their interaction threshold. Their relic abundance today would naturally explain dark matter's observed cosmic density. Supersymmetry, a theoretical extension of the standard model, predicts several WIMP candidates. The lightest supersymmetric particle, often the neutralino, would be stable and weakly interacting perfect properties for dark matter. Supersymmetric theory suggests that every known particle has a heavier supersymmetric partner with different quantum properties. While no supersymmetric particles have been detected despite decades of accelerator searches, they remain viable dark matter candidates if their masses exceed current experimental limits. Alternative dark matter candidates include sterile neutrinos, hypothetical particles similar to ordinary neutrinos but without weak force interactions. Axions, proposed to solve certain problems in quantum chromodynamics, would be extremely light particles that interact with electromagnetic fields only under special conditions. Primordial black holes formed in the early universe could provide gravitating dark matter without requiring exotic particles at all. Yet, each of these candidates faces theoretical challenges or observational constraints. WIMPs should produce detectable signals in underground detectors, but decades of increasingly sensitive searches have found no evidence of WIMP interactions. Sterile neutrinos would decay into ordinary neutrinos and photons, potentially producing observable X-ray emissions. Axions require specific electromagnetic conditions to convert into photons, and dedicated experiments have found no evidence of axion dark matter. The mystery deepens when we consider dark matter's observed properties. Gravitational lensing reveals that dark matter can form dense concentrations without ordinary matter, suggesting it can interact gravitationally with itself. Yet it doesn't appear to dissipate energy through electromagnetic radiation, implying either very weak self-interactions or electromagnetic neutrality. Dark matter halos extend far beyond the visible edges of galaxies, indicating that dark matter doesn't lose energy and collapse like ordinary matter. Some theoretical models propose that dark matter possesses its own dark photons, force-carrying particles that mediate interactions between dark matter particles while remaining hidden from ordinary electromagnetic fields. This could allow dark matter to have complex internal physics while maintaining electromagnetic invisibility. Other models suggest that dark matter interactions change with cosmic epoch, allowing structure formation in the early universe while maintaining invisibility today. The quantum mechanical foundations of particle interactions provide crucial insights into dark matter's electromagnetic silence. In quantum field theory, forces arise from symmetries in the laws of physics. The electromagnetic force emerges from gauge symmetry, the requirement that physical laws remain unchanged under certain mathematical transformations. Particles acquire electric charge through their coupling to this gauge symmetry. If dark matter particles don't couple to electromagnetic gauge symmetry, they would remain forever invisible to electromagnetic radiation. This suggests that dark matter might represent a fundamentally different class of matter particles that participate in gravitational interactions, but remain outside the electromagnetic sector of particle physics. Understanding why requires us to examine how particles acquire their fundamental properties through interactions with quantum fields that permeate all of space. The answers lie in the deepest level of reality, where quantum fields create the fundamental properties that determine whether matter can ever touch light. Chapter 4. Quantum Silence. At the most fundamental level of reality, particles don't exist as tiny billiard balls bouncing through space. They emerge as excitations in quantum fields, invisible, mathematical entities that permeate every point in the universe. The electron field exists everywhere, and what we call an electron is simply a localized vibration in this field. The photon field mediates electromagnetic interactions, creating the light we see when its excitations propagate through space. Understanding dark matter's electromagnetic silence requires diving into this quantum field reality, where the deepest laws of physics determine which fields can talk to each other and which must remain forever mute. Quantum field theory reveals that all particle interactions occur through field couplings, mathematical relationships that allow one field to influence another. The electromagnetic field couples to any particle field that carries electric charge, creating the interactions we observe as electromagnetic phenomena. When an electron field excitation, an electron, interacts with the electromagnetic field, it can emit or absorb photons, creating the electromagnetic radiation we detect throughout the universe. The strength of these couplings is governed by fundamental constants that appear fixed throughout space and time. The fine structure constant, approximately 137th, determines how strongly charged particles interact with electromagnetic fields. This seemingly arbitrary number governs everything from the stability of atoms to the brightness of stars. Yet quantum field theory provides no explanation for why this constant has the value it does. It is simply a measured parameter that describes our universe's electromagnetic behavior. What makes dark matter's electromagnetic silence so profound is that it appears to have zero coupling to the electromagnetic field. Not merely weak coupling like neutrinos, but absolute zero, a complete absence of electromagnetic interaction that extends across all energy scales and cosmic epochs. In quantum field theory terms, dark matter particles would belong to field representations that have no electromagnetic charge quantum number whatsoever. This electromagnetic isolation could arise through several quantum mechanisms. The most straightforward possibility is that dark matter particles simply lack the quantum properties necessary for electromagnetic coupling. Just as photons don't carry electric charge and therefore don't interact directly with each other except through quantum loop corrections, dark matter particles might lack any quantum numbers that couple to electromagnetic fields. Consider how quantum symmetries determine particle interactions. The Standard Model is built on local gauge symmetries, mathematical requirements that physical laws remain unchanged under certain transformations at every point in space and time. Electromagnetic interactions arise from U1 gauge symmetry, which requires that physics remains invariant under phase rotations of complex valued particle fields. Particles acquire electric charge through their coupling to this gauge symmetry, with the charge value determining interaction strength. If dark matter belongs to quantum field representations that don't couple to U1 electromagnetic gauge symmetry, it would remain electromagnetically neutral by construction. This isn't simply charge neutrality like neutrons possess. It's gauge invisibility, a complete absence of electromagnetic quantum numbers that prevents any form of electromagnetic interaction, direct or indirect. The quantum vacuum itself provides insights into electromagnetic silence. Even empty space teems with virtual particle fluctuations, quantum field excitations that briefly appear and disappear on timescales set by Heisenberg's uncertainty principle. These virtual particles can mediate forces between real particles, creating measurable effects like the Casimir force between conducting plates. Ordinary matter interacts with virtual photons constantly, creating quantum corrections to electromagnetic interactions that have been measured with extraordinary precision. Yet dark matter appears immune to these quantum electromagnetic fluctuations. If dark matter particles truly don't couple to electromagnetic fields, they wouldn't interact with virtual photons and would remain unaffected by quantum electromagnetic phenomena. This electromagnetic immunity would extend to all quantum field theory processes involving photons, making dark matter invisible to the vast majority of high-energy physics experiments. Supersymmetric theories offer one framework for understanding electromagnetic silence. In these models, dark matter candidates like neutralinos arise as superpositions of neutral gauge bosons and Higgs bosons. While these particles can interact through weak nuclear forces, they possess no electromagnetic charge and couple only weakly to photons through quantum loop processes. Even these indirect electromagnetic interactions could be suppressed if the supersymmetric particle masses are large enough. Alternative models propose that dark matter belongs to entirely separate gauge sectors with their own hidden forces and force-carrying particles. These dark sector models suggest that dark matter particles interact through dark photons, gauge bosons similar to ordinary photons, but mediating forces only between dark matter particles. The dark electromagnetic field would be orthogonal to our electromagnetic field, creating a parallel realm of electromagnetic phenomena that remains hidden from ordinary matter. String theory cosmological models provide another perspective on electromagnetic silence. In these frameworks, our universe might be a three-dimensional brane embedded in higher dimensional space, with standard model particles confined to the brane while gravity propagates through all dimensions. Dark matter could consist of particles that live in extra dimensions or on parallel branes, interacting with our brane only through gravitational forces that extend into the extra dimensions. Quantum mechanics also suggests that electromagnetic silence can emerge from topological protection, quantum mechanical mechanisms that prevent certain interactions from occurring, even if they were otherwise allowed by symmetry. Topological insulators in condensed matter physics demonstrate how quantum phases can create electromagnetic immunity for certain excitations while allowing other electromagnetic phenomena to occur normally. The cosmological implications of quantum electromagnetic silence are profound. During the early universe's radiation-dominated epoch, ordinary matter and photons maintained thermal equilibrium through continuous electromagnetic interactions. Protons, electrons, and photons scattered off each other frequently, creating a hot, dense plasma that remained opaque to electromagnetic radiation. Dark matter, with its electromagnetic immunity, would have remained kinetically decoupled from this thermal bath, evolving independently according to gravitational dynamics alone. This electromagnetic decoupling explains why dark matter can form extended halos around galaxies. While ordinary matter loses energy through electromagnetic radiation and collapses into stars and planets, dark matter maintains its kinetic energy indefinitely. The absence of electromagnetic cooling allows dark matter to support diffuse gravitational structures that extend far beyond the visible edges of galaxies. Quantum field theory predicts that electromagnetically silent particles could still interact through other fundamental forces. Dark matter might interact through weak nuclear forces, creating rare scattering events with atomic nuclei that underground detectors hope to observe. Alternatively, dark matter might possess its own hidden forces that govern self-interactions while remaining invisible to electromagnetic probes. The search for dark matter has become a quest to detect particles that interact through non-electromagnetic channels. Direct detection experiments use massive underground detectors to catch the rare occasions when dark matter particles might scatter off atomic nuclei through weak interactions. Indirect detection searches look for the electromagnetic signatures of dark matter annihilation, hoping that dark matter particles might occasionally convert their mass into observable radiation. Yet decades of increasingly sensitive searches have found no evidence of dark matter interactions beyond gravity. This observational void suggests that dark matter's electromagnetic silence might extend to other forces as well, creating particles that interact almost exclusively through gravitational fields. Such gravitationally interacting massive particles would be nearly impossible to detect directly, revealing themselves only through their cumulative gravitational effects on cosmic structure. The quantum mechanical foundations of electromagnetic silence point toward a deep truth about the nature of physical reality. The universe might contain entire sectors of matter that remain forever hidden from electromagnetic observation, interacting with our visible cosmos only through the geometric curvature of spacetime itself. Understanding this hidden realm requires us to examine gravity's unique role among the fundamental forces and why gravitational interaction alone might be sufficient to shape cosmic evolution. Chapter 5. Gravitational monopoly. Gravity is the universe's strangest force, simultaneously the weakest and most influential of nature's four fundamental interactions. A refrigerator magnet can overcome Earth's entire gravitational field when it lifts a paper clip, demonstrating how feeble gravity is compared to electromagnetic forces. Yet gravity alone shapes the largest structures in the cosmos, from solar systems to galaxy clusters spanning hundreds of millions of light years. For dark matter, gravity isn't just one force among many. It appears to be the only force that matters, creating a cosmic relationship built entirely on spacetime curvature. Einstein's general relativity revealed that gravity isn't actually a force in the traditional sense. Instead, mass and energy curve the geometry of spacetime itself, and objects follow the straightest possible paths through this curved geometry. What we perceive as gravitational attraction is really matter following geodesics, the four-dimensional equivalent of straight lines, through the warped fabric of spacetime. This geometric interpretation of gravity has profound implications for dark matter, suggesting that gravitational interaction requires only the possession of mass energy, not participation in any gauge symmetry or force-carrying particle exchange. Unlike the other fundamental forces, gravity couples universally to all forms of mass energy. Electromagnetic forces require electric charge, strong nuclear forces require color charge, and weak nuclear forces require weak isospin. But gravity responds to mass energy in all its forms: kinetic energy, potential energy, binding energy, and even the mass equivalent of other forces themselves. This universal coupling means that any particle with mass will gravitationally influence spacetime, regardless of its other properties or interactions. The weakness of gravity makes this universality possible. While electromagnetic forces between charged particles can overwhelm gravitational attraction over short distances, gravity's infinite range and always attractive nature allow it to dominate on cosmic scales. Two protons repel each other electromagnetically with a force that's yp times stronger than their gravitational attraction. But over galactic distances, gravity's cumulative effect becomes the only force that matters. For dark matter, this gravitational monopoly creates a unique cosmic role. If dark matter particles interact only through gravity, they would still profoundly influence cosmic evolution through their gravitational effects on spacetime geometry. The massive dark matter would curve spacetime around galaxies, creating gravitational wells that affect the motion of ordinary matter and light. This explains how we can detect dark matter's presence through gravitational lensing, even though it remains electromagnetically invisible. The cosmic microwave background radiation provides spectacular evidence of dark matter's gravitational influence during the universe's early epochs. When the universe was only 380,000 years old, it had cooled enough for electrons and protons to combine into neutral hydrogen atoms, making space transparent to electromagnetic radiation for the first time. The photons released during this recombination epoch still permeate the universe today as the cosmic microwave background, carrying information about conditions in the primordial cosmos. Temperature fluctuations in this ancient radiation reveal the gravitational fingerprints of dark matter. Regions with slightly higher dark matter density created deeper gravitational wells that affected the temperature and polarization of photons passing through them. The precise pattern of these fluctuations, measured by satellites like WMAP and Planck, allows cosmologists to determine dark matter's abundance with extraordinary precision while learning nothing about its electromagnetic properties. These observations confirm that dark matter was already gravitationally significant during the universe's first few 100,000 years, long before the first stars ignited. Dark matter's gravitational influence helped ordinary matter collapse into the dense regions where stars and galaxies would eventually form. Without dark matter's gravitational scaffolding, the universe might have remained a smooth sea of hydrogen and helium with no dense structures to enable star formation and galactic evolution. The gravitational-only interaction explains several puzzling aspects of dark matter's cosmic behavior. Dark matter halos extend far beyond the visible edges of galaxies, creating gravitational influence zones much larger than stellar distributions. If dark matter interacted electromagnetically, it would lose energy through radiation and collapse toward galactic centers like ordinary matter. Instead, dark matter maintains extended distributions that provide stable gravitational frameworks for galactic dynamics. Computer simulations of cosmic structure formation demonstrate how gravity alone can create complex dark matter architectures. Starting from tiny quantum fluctuations in the early universe, gravitational instability causes dark matter to collapse into a cosmic web of filaments, nodes, and halos. These simulations, which include only gravitational interactions, successfully reproduce the observed large-scale structure of the universe, from the distribution of galaxy clusters to the properties of dark matter halos around individual galaxies. The mathematics of gravitational interaction reveals why electromagnetic silence doesn't prevent cosmic significance. In general relativity, the stress-energy tensor describes how mass, energy, momentum, and stress curve spacetime. Dark matter contributes to this tensor through its mass, energy, density, and pressure, creating space-time curvature that affects everything from planetary orbits to the propagation of light across cosmic distances. The fact that dark matter doesn't participate in electromagnetic interactions is irrelevant to its gravitational influence. Mass curves spacetime regardless of how it interacts with other forces. This gravitational monopoly also explains why dark matter detection remains so challenging. Direct detection experiments rely on non-gravitational interactions between dark matter particles and ordinary matter to create observable signals. If dark matter truly interacts only through gravity, these experiments would never detect individual dark matter particles because gravitational forces between single particles are unimaginably weak. Only the cumulative gravitational effect of vast amounts of dark matter becomes observationally significant. Consider the gravitational force between a dark matter particle and an atomic nucleus in an underground detector. Yet gravity's weakness becomes strength on cosmic scales. While individual particle gravitational interactions remain undetectable, the gravitational field of a galaxy's dark matter halo influences every star in the galactic disk. The orbital velocities of these stars provide a sensitive probe of the total gravitating mass, revealing dark matter's presence through its cumulative gravitational effect, even though individual dark matter particles remain undetected. The study of galaxy mergers provides additional evidence for dark matter's gravitational-only interactions. When two galaxies collide, their ordinary matter experiences electromagnetic friction that causes gas clouds to slow down and eventually merge. Dark matter, immune to electromagnetic forces, passes through collision regions with minimal interaction, creating temporary spatial separation between ordinary matter and dark matter components. Observations of colliding galaxy clusters like the Bullet cluster clearly show this gravitational electromagnetic decoupling, with dark matter, traced by gravitational lensing, separated from ordinary matter, traced by X-ray emission. These collision studies reveal that dark matter's self-interactions, if they exist at all, must be extremely weak. Strong dark matter self-interactions would cause dark matter to slow down during collisions just like ordinary matter does. The observed separation between dark matter and ordinary matter in merging systems constrains dark matter self-interaction cross-sections to be much smaller than ordinary matter interaction rates. Theoretical models of gravitational-only dark matter explore various particle physics scenarios that could produce such behavior. Sterile neutrinos, if they exist, would interact gravitationally but remain electromagnetically invisible. Primordial black holes would interact only through gravity while remaining completely dark to electromagnetic observations. Exotic particles from string theory or extra-dimensional models could interact gravitationally, while being geometrically isolated from standard model force fields. The gravitational monopoly reveals a profound aspect of cosmic architecture, the universe's largest structures are held together by its weakest force, mediated by matter that remains invisible to its most versatile force. This cosmic irony suggests that our electromagnetic universe, despite its rich complexity and observational accessibility, represents only a small fraction of gravitational reality. Understanding how this hidden gravitational cosmos shapes the visible universe requires examining the cosmic dance between matter and radiation across cosmic history. Chapter 6: Cosmic Cooling. The universe began as a fiery democracy where matter and radiation shared energy through constant electromagnetic interaction. But it evolved into a cosmic oligarchy where dark matter as electromagnetic silence granted it dominion over structure formation. This transformation from radiation-dominated equality to matter-dominated hierarchy represents one of the most profound phase transitions in cosmic history, fundamentally altering how energy flows through space-time and determining whether galaxies could ever form at all. In the universe's first 50,000 years, radiation ruled supreme. Photons carried more energy density than matter, and their intense electromagnetic interactions with charged particles created a tightly coupled plasma where matter and radiation moved together as a single fluid. Electrons and protons scattered off photons constantly, preventing electromagnetic radiation from traveling more than a few centimeters before being absorbed or deflected. This cosmic fog made the early universe completely opaque, a blazing furnace where no structure could form because radiation pressure overwhelmed gravitational attraction. But dark matter experienced this epoch entirely differently. Without electromagnetic interactions, dark matter particles couldn't scatter off photons or exchange energy with the radiation field. While ordinary matter remained locked in electromagnetic thermal equilibrium with radiation, dark matter evolved according to purely gravitational dynamics. Dark matter could begin gravitational collapse immediately after inflation ended, starting the structure formation process, while ordinary matter remained trapped in electromagnetic prison. The cosmic microwave background radiation preserves evidence of this electromagnetic tyranny. Temperature fluctuations in this ancient light reveal acoustic oscillations, compression waves that propagated through the coupled matter radiation fluid in the early universe. These baryon acoustic oscillations created a characteristic pattern of peaks and valleys in the CMB temperature spectrum, precisely matching theoretical predictions for a universe where ordinary matter and photons move together under radiation pressure. Dark matter's gravitational influence appears in these same CMB observations, but through different physical mechanisms. While ordinary matter participated in acoustic oscillations driven by radiation pressure, dark matter accumulated in gravitational potential wells without electromagnetic resistance. This created a gravitational framework that influenced ordinary matter's acoustic oscillations, leaving subtle imprints in the CMB that reveal dark matter's abundance and clustering properties. The transition from radiation dominance to matter dominance occurred roughly 50,000 years after the Big Bang, when the universe had expanded and cooled enough that matter's energy density exceeded radiation's energy density. This epochal shift fundamentally changed cosmic dynamics, but ordinary matter remained electromagnetically coupled to radiation for another 330,000 years. Dark matter had already enjoyed tens of thousands of years of pure gravitational evolution by the time ordinary matter achieved electromagnetic freedom. Recombination, the epoch when electrons and protons combined into neutral hydrogen atoms, finally liberated ordinary matter from electromagnetic bondage. With free electrons removed from the cosmic plasma, photons could travel vast distances without scattering, making the universe transparent for the first time. The cosmic microwave background radiation we observe today consists of these liberated photons, redshifted by cosmic expansion from visible light to microwave frequencies. But recombination created an even more fundamental transformation. It eliminated electromagnetic drag on ordinary matter motion. Free electrons in plasma can scatter off photons, creating electromagnetic friction that prevents gravitational collapse. Once electrons bound into neutral atoms, this electromagnetic resistance disappeared, allowing ordinary matter to fall into the gravitational wells the dark matter had been excavating for hundreds of thousands of years. This electromagnetic liberation explains why the first stars couldn't form until several 100 million years after the Big Bang. Even after recombination freed ordinary matter from electromagnetic coupling to radiation, gravity still had to overcome the kinetic energy that thermal motion had imparted to matter during the radiation-dominated epoch. Dark matter, with its head start in gravitational collapse, provided the gravitational scaffolding that allowed ordinary matter to eventually condense into stars and galaxies. Computer simulations reveal how this electromagnetic cooling shaped cosmic evolution. Dark matter simulations that include only gravitational interactions reproduce the observed large-scale structure of the universe with remarkable accuracy. Adding ordinary matter with its electromagnetic interactions creates the detailed physics of star formation, galactic dynamics, and the intergalactic medium. The combination produces a universe where dark matter provides gravitational architecture, while ordinary matter creates the electromagnetic phenomena we observe. The contrast between electromagnetically active and electromagnetically silent matter becomes even more dramatic during later cosmic epochs. As the universe continued expanding and cooling, ordinary matter began forming increasingly complex electromagnetic structures. Gravitational collapse heated gas clouds until they reached temperatures sufficient for nuclear fusion, igniting the first stars. These stellar furnaces converted hydrogen and helium into heavier elements while producing vast amounts of electromagnetic radiation. Stellar radiation fundamentally altered the electromagnetic environment throughout the universe. Ultraviolet light from massive stars reionized hydrogen atoms that had formed during recombination, creating bubbles of ionized gas around early stellar populations. This cosmic reionization made space partially opaque to certain wavelengths of light, creating new electromagnetic interactions between matter and radiation. Yet dark matter remained completely unaffected by this electromagnetic transformation. The electromagnetic cooling of ordinary matter through stellar radiation enabled the formation of planets, solar systems, and eventually life itself. Stars lose energy through electromagnetic radiation, allowing them to maintain nuclear fusion while slowly converting mass into light. Planets form when electromagnetic forces bind atoms into molecules and solid materials. The chemistry that makes biology possible depends entirely on electromagnetic interactions between electrons in different atomic orbitals. Meanwhile, dark matter maintains its gravitational influence without participating in any of these electromagnetic processes. Dark matter halos provide the gravitational wells where galaxies form, but they remain diffuse and extended because dark matter cannot radiate energy electromagnetically. This creates a cosmic division of labor. Dark matter provides gravitational architecture, while ordinary matter creates complex electromagnetic structures within that gravitational framework. The ongoing expansion of the universe adds another layer to this electromagnetic cooling story. As space expands, the wavelength of electromagnetic radiation stretches, reducing photon energy density through cosmological redshift. This cosmic cooling means that electromagnetic interactions become progressively less important for cosmic dynamics as the universe ages. Matter dominates over radiation today by a factor of roughly 3,000, but this ratio continues growing as expansion dilutes radiation energy. Dark matter, as gravitational dominance, actually increases with cosmic time because gravity becomes relatively stronger as electromagnetic radiation loses energy to cosmic expansion. In the far future, when stellar formation ends and existing stars burn out, electromagnetic radiation will become essentially irrelevant to cosmic dynamics. The universe will enter a truly dark matter-dominated epoch where gravitational interactions alone govern cosmic evolution. This cosmic cooling timeline reveals why dark matter's electromagnetic silence is so cosmologically significant. While electromagnetic interactions create the rich complexity of chemistry, biology, and technological civilization, they represent only a brief phase in cosmic evolution. Dark matter has gravitational patience, its ability to maintain influence without electromagnetic energy loss makes it the universe's ultimate architect of large-scale structure. The implications extend beyond cosmic structure formation to the fundamental nature of physical reality itself. Electromagnetic interactions create the observational accessibility that allows us to study the universe through light, but they also represent a cosmic minority viewpoint. The vast majority of cosmic matter experiences reality through purely gravitational interaction, suggesting that our electromagnetic perspective might fundamentally limit our understanding of cosmic evolution. But electromagnetic cooling isn't just a cosmic historical process. It is an ongoing phenomenon that continues shaping the universe today. Understanding how matter loses energy through electromagnetic radiation while dark matter maintains its gravitational influence reveals profound insights about cosmic destiny and the ultimate fate of structure in an expanding universe. Chapter 7. Hidden Interactions. While dark matter maintains electromagnetic silence that has persisted for over 13 billion years, this doesn't necessarily mean it's completely inert. Hidden beneath the electromagnetic void might lie an entire realm of dark forces, interactions between dark matter particles that remain invisible to our electromagnetic universe, while potentially creating complex physics within the dark sector itself. This possibility has led theoretical physicists to explore models where dark matter possesses its own rich interaction network, complete with dark photons, dark gauge forces, and dark phase transitions that shape dark matter's cosmic behavior while remaining hidden from ordinary matter. The concept of dark forces emerges naturally from particle physics symmetry principles. If ordinary matter can interact through electromagnetic, weak, and strong forces mediated by photons, W and Z bosons and gluons respectively. Why couldn't dark matter possess its own set of force-carrying particles? These dark gauge bosons would mediate interactions exclusively between dark sector particles, creating a parallel realm of fundamental forces that remains orthogonal to standard model interactions. Dark photons represent the simplest example of hidden interactions. Just as ordinary photons mediate electromagnetic forces between electrically charged particles, dark photons could mediate dark electromagnetic forces between particles carrying dark charge, a quantum number that couples to dark gauge fields instead of ordinary electromagnetic fields. Dark matter particles could possess dark electric charge while maintaining zero ordinary electric charge, allowing them to interact electromagnetically within the dark sector while remaining invisible to ordinary light. The mathematical structure of dark forces mirrors ordinary gauge theories with crucial differences. While ordinary electromagnetism emerges from U1 gauge symmetry with photons as massless force carriers, dark electromagnetism might involve massive dark photons or different gauge groups entirely. These variations could create dark forces with shorter ranges than ordinary electromagnetism or different coupling strengths that govern dark matter interaction rates. Astronomical observations provide subtle hints that dark interactions might actually exist. Computer simulations that include only gravitational interactions between dark matter particles predict dark matter halo profiles that are more centrally concentrated than observed galactic rotation curves suggest. This Corcus problem could be resolved if dark matter particles undergo weak self-interactions that transfer energy and reduce central density concentrations. Similarly, the satellite problem in cosmological simulations suggests that pure gravity-only dark matter creates too many small dark matter subhalos around large galaxies compared to observed satellite galaxy populations. Dark interactions could suppress small-scale structure formation or modify dark matter clustering properties in ways that better match observations. However, these hints remain controversial, and alternative explanations involving ordinary matter physics, stellar feedback, supernova explosions might equally well explain these apparent discrepancies. The broader searches for dark forces focus on detecting dark photons that might occasionally convert into ordinary photons under special conditions. If dark photons have small masses and couple weakly to ordinary electromagnetic fields, they could convert into detectable radiation when passing through strong magnetic fields or interacting with cavity resonators. Several experiments have searched for such dark photon signatures without finding convincing evidence, constraining the strength of any dark photon coupling to ordinary matter. Theoretical models of dark interactions often invoke kinetic mixing, quantum field theory processes that create small connections between dark and ordinary electromagnetic fields. Even if dark matter particles don't carry ordinary electric charge, quantum loop corrections could generate tiny couplings between dark photons and ordinary photons. These interactions would be extraordinarily weak, but might be detectable in precision experiments or could leave subtle signatures in cosmic observations. The possibility of dark phase transitions adds another layer of complexity to hidden dark matter physics. Just as ordinary matter undergoes phase transitions, water freezing into ice, electromagnetic symmetry breaking in superconductors, dark matter might experience its own phase transitions driven by dark force dynamics. A dark phase transition in the early universe could have affected dark matter clustering properties or created dark matter density fluctuations that influence large-scale structure formation. Some models propose that dark matter consists of composite particles bound together by dark forces, similar to how protons and neutrons are composed of quarks bound by strong forces. These dark atoms, or molecules, could have complex internal structures and excited states while remaining electromagnetically neutral. Dark force interactions could govern the binding energies and stability of these composite dark particles. The asymmetric dark matter paradigm suggests even more sophisticated dark sector physics. In these models, a cosmic asymmetry between dark matter and dark antimatter, similar to the matter-antimatter asymmetry in the ordinary sector, creates stable dark matter relics while dark antimatter annihilates away. This requires dark interactions sophisticated enough to generate and preserve particle-antiparticle asymmetries, potentially involving dark weak forces, dark CP violation, and dark baryogenesis mechanisms. Observational tests for dark interactions exploit their gravitational consequences despite electromagnetic invisibility. Self-interacting dark matter models predict that frequent dark particle collisions would modify the shapes of dark matter halos, creating rounder profiles in high-density regions where collision rates are enhanced. Galaxy cluster observations can test these predictions by comparing dark matter distributions measured through gravitational lensing with the predicted effects of dark self-interactions. The bullet cluster collision provides particularly stringent constraints on dark interaction strength. When two galaxy clusters collide, ordinary matter experiences electromagnetic drag that slows it down, but dark matter should pass through relatively unimpeded if dark interactions are weak. Observations confirm this expectation, with dark matter, traced by gravitational lensing, clearly separated from ordinary matter, traced by X-ray emission. However, the spatial separation is consistent with modest dark self-interactions, leaving room for weak dark forces. Stellar dynamics in dwarf galaxies offer another probe of dark interactions. These small, dark matter-dominated galaxies provide clean laboratories for testing dark matter physics because stellar feedback effects are minimal. If dark interactions transfer energy between dark matter particles, they should create observable signatures in stellar kinematics and galaxy structure. Current observations are consistent with collisionless dark matter, but have insufficient precision to rule out weak dark interactions. The search for dark matter in underground detectors could be sensitive to dark force effects, even if dark matter doesn't interact directly with ordinary matter. If dark matter particles occasionally interact with each other through dark forces, these interactions could change dark matter velocities or energy distributions in ways that affect detection rates. Dark interactions might also catalyze dark matter capture in massive objects like the Earth or Sun, potentially enhancing indirect detection signals. Cosmological structure formation simulations increasingly include dark interaction effects to test their observational consequences. These sophisticated unbody simulations follow billions of dark matter particles through cosmic time, while including both gravitational dynamics and hypothetical dark force interactions. By varying dark interaction strength and comparing results with observations, cosmologists can constrain the properties of any hidden dark sector physics. The theoretical landscape of dark interactions extends far beyond simple dark electromagnetism. Models involving dark QCD, dark quantum chromodynamics, propose dark matter composed of dark quarks bound by dark gluons into dark hadrons. Dark weak interactions could govern dark matter stability and decay processes. Some theories even suggest that dark matter might experience all four fundamental forces in dark versions: dark gravity, dark electromagnetism, dark weak interactions, and dark strong interactions. Yet the observational evidence for dark interactions remains ambiguous at best. Most astronomical and cosmological observations are consistent with collisionless dark matter that interacts only gravitationally. The electromagnetic silence of dark matter has persisted across cosmic time, suggesting that any dark interactions must be either extremely weak or occur through mechanisms that do produce observable electromagnetic signatures. This hidden realm of potential dark physics highlights how much we still do not understand about the universe as dominant component. Dark matter's electromagnetic silence might conceal a rich tapestry of dark forces and dark particles, or it might reflect genuinely minimal physics involving only gravitational interactions. Unraveling these hidden interactions, if they exist, requires pushing observational, astronomy, and experimental physics to their limits, while exploring the deepest theoretical frameworks for understanding the fundamental nature of matter and forces. Chapter 8. Detection Challenges. Searching for dark matter represents the ultimate needle in a haystack challenge, except the needle is invisible. The haystack spans the entire universe, and we're not even certain what constitutes a successful detection. For over 4 decades, physicists have constructed increasingly sophisticated experiments to catch dark matter particles in the act of interacting with ordinary matter. But dark matter's electromagnetic silence makes it extraordinarily elusive. Every detection strategy must overcome the fundamental challenge that dark matter particles can pass through vast amounts of ordinary matter without leaving any electromagnetic trace. The most direct approach involves underground laboratories buried miles beneath the Earth's surface, shielded from cosmic radiation by millions of tons of rock. These facilities house ultra-sensitive detectors designed to record the rare occasions when a dark matter particle might scatter off an atomic nucleus through weak nuclear force interactions. The detectors themselves are marvels of precision engineering. Ultra-pure germanium crystals, liquid xenon chambers, and crystalline scintillators cooled to temperatures just above absolute zero to minimize thermal noise. The challenge is immense because the expected interaction rates are vanishingly small. Current theoretical models predict that a dark matter particle might scatter off detector nuclei perhaps once per year per kilogram of detector material. Since dark matter particles are constantly streaming through these detectors at velocities of hundreds of kilometers per second, this means that trillions of dark matter particles pass through each detector daily while leaving no detectable signature whatsoever. Even when interactions do occur, the signatures are subtle. A dark matter particle collision with a nucleus would transfer only a tiny amount of kinetic energy equivalent to the energy released when an atom vibrates at room temperature. Distinguishing these minute energy deposits from background radiation, thermal fluctuations, and electromagnetic interference requires extraordinary experimental precision and sophisticated data analysis techniques. The electromagnetic nature of detector technology creates additional challenges for detecting electromagnetically silent dark matter. All particle detectors ultimately rely on electromagnetic processes to convert particle interactions into observable signals. Ionization detectors measure the electromagnetic radiation produced when energetic particles strip electrons from atoms. Scintillation detectors convert particle energy into light photons that can be measured by photomultiplier tubes. Even gravitational wave detectors use electromagnetic laser interferometry to measure spacetime distortions. This electromagnetic dependence means that dark matter detection requires a two-step process. First, a rare non-electromagnetic interaction between dark matter and detector nuclei, followed by electromagnetic amplification of the resulting signal. The weakness of non-electromagnetic interactions, combined with the need for electromagnetic signal processing, creates a detection challenge unlike any other in experimental physics. The Large Hadron Collider pursues an alternative detection strategy by attempting to create dark matter particles in high-energy proton collisions. If dark matter particles can be produced through ordinary standard model interactions, they might be created in the extreme energies achieved when protons collide at nearly the speed of light. Since dark matter particles would immediately escape the detector without electromagnetic interaction, physicists look for missing energy, cases where the collision energy budget doesn't balance when only electromagnetically interacting particles are accounted for. Yet even this approach faces fundamental limitations imposed by dark matter's electromagnetic silence. The LHC can only detect dark matter production indirectly through missing energy signatures, which can also result from neutrinos or experimental uncertainties. Distinguishing dark matter production from other sources of missing energy requires statistical analysis of thousands of collision events, looking for patterns that might reveal dark matter's presence. Space-based gamma-ray observatories like the Fermi Large Area Telescope search for indirect evidence of dark matter through the electromagnetic radiation produced when dark matter particles annihilate or decay. Some theoretical models predict that dark matter particles are their own antiparticles, meaning that when two dark matter particles collide, they could annihilate into ordinary particles that produce detectable gamma rays, neutrinos, or cosmic ray particles. The irony of indirect detection is that it relies on dark matter's occasional violation of electromagnetic silence. For indirect detection to work, dark matter must sometimes convert into electromagnetically interacting particles through annihilation or decay processes. Yet these same processes, if they occurred frequently, would violate dark matter's observed stability and electromagnetic invisibility over cosmic timescales. Axion detection experiments exploit a different theoretical possibility, that dark matter consists of extremely light particles called axions that can occasionally convert into photons under specific electromagnetic conditions. The Axion dark matter experiment, a DMX, uses powerful superconducting magnets to create electromagnetic fields that might catalyze axion to photon conversion. These experiments search for the faint electromagnetic signals that would result if the dark matter pervading our galactic neighborhood consists of axions. Even gravitational detection faces challenges despite gravity being the one force that definitely couples to dark matter. While we can detect dark matter's cumulative gravitational effects on cosmic scales, detecting the gravitational influence of individual dark matter particles remains far beyond current technological capabilities. The gravitational force between a dark matter particle and an ordinary atom is weaker than electromagnetic forces by a factor of 1036, making direct gravitational detection essentially impossible. The null results from decades of dark matter searches have forced physicists to confront unsettling possibilities about dark matter's true nature. Perhaps dark matter interacts even more weakly with ordinary matter than current theories predict, making detection impossible with foreseeable technology. Perhaps dark matter belongs to an entirely hidden sector of particle physics with no standard model interactions beyond gravity. Or perhaps dark matter consists of primordial black holes or other exotic objects that don't involve new particle physics at all. Each negative result constrains the properties dark matter can possess while highlighting the experimental challenges of detecting electromagnetically silent matter. The Lux Zeppelin experiment, one of the most sensitive dark matter detectors ever constructed, can detect nuclear recoils equivalent to roughly 1/100th the rest mass energy of an electron. Yet even this extraordinary sensitivity might be insufficient if dark matter interactions are weaker than current theoretical expectations. The cosmic abundance of dark matter adds another layer of detection complexity. While dark matter comprises 85% of all matter in the universe, its density in our local cosmic neighborhood is roughly equivalent to 1 proton mass per cubic centimeter. This means that sensitive dark matter detectors, despite their large masses and extended operation periods, contain relatively few dark matter particles at any given time. Furthermore, dark matter's velocity distribution affects detection prospects in subtle ways. Dark matter particles in our galactic neighborhood move with velocities of roughly 200–300 kilometers per second due to our galaxy's rotation and the solar system's motion through the galactic dark matter halo. These velocities determine the kinetic energies available for dark matter nucleus, scattering and affect the direction and magnitude of any detection signals. Seasonal variations in Earth's orbital velocity around the Sun create small modulations in dark matter detection rates that some experiments claim to observe. As Earth's orbital motion alternately aligns with and opposes the solar system's motion through the galactic dark matter halo, the relative velocity between dark matter particles and terrestrial detectors varies by roughly 30 kilometers per second. This creates annual modulation patterns that might provide distinctive signatures of dark matter detection. Yet even these subtle effects remain controversial, because electromagnetic backgrounds also vary seasonally due to atmospheric changes, cosmic ray fluctuations, and detector temperature variations. Distinguishing genuine dark matter signals from electromagnetic contamination requires years of careful data collection and analysis, with multiple independent experiments needed to confirm any claimed detection. The search for dark matter has become a technological arms race, pushing experimental physics to its absolute limits. Future experiments will employ even larger detector masses, deeper underground locations, and more sophisticated background rejection techniques. Proposed detectors involving tens of tons of ultra-pure target material operating for decades might finally achieve the sensitivity needed to detect dark matter interactions. But dark matter's electromagnetic silence means that even successful detection would provide limited information about dark matter's fundamental properties. Unlike electromagnetic radiation, which carries detailed information about its source's composition, temperature, and motion, the dark matter interactions would reveal only basic properties like particle mass and interaction cross-section. Understanding dark matter's true nature might require detection through multiple channels combined with theoretical insights into hidden sector particle physics. The ultimate irony of dark matter detection is that success might raise more questions than it answers, revealing the existence of a vast hidden realm of physics while providing only glimpses of its true complexity and significance for cosmic evolution. Chapter 9: Theoretical Frontiers. The failure to detect dark matter particles directly has pushed theoretical physics into uncharted territory, forcing scientists to question fundamental assumptions about matter, forces, and the very nature of physical reality. Beyond the Standard Model lies a vast landscape of theoretical possibilities, from mirror worlds that duplicate our entire electromagnetic universe to extra dimensions where dark matter hides in geometric spaces we cannot directly perceive. These theoretical frontiers represent humanity's most ambitious attempts to understand how the majority of cosmic matter can remain forever hidden from electromagnetic observation. String theory, the most comprehensive framework for unifying all fundamental forces, predicts that our four-dimensional spacetime might be embedded in a higher dimensional reality with as many as 11 total dimensions. In these models, ordinary matter could be confined to a three-dimensional brane, short for membrane, floating in higher dimensional space, while gravity propagates through all dimensions. Dark matter might consist of particles that live in extra dimensions or unparalleled branes, interacting with our brain primarily through gravitational forces that extend into the additional spatial dimensions. This higher dimensional scenario elegantly explains dark matter's electromagnetic silence. If dark matter particles exist in extra dimensions that ordinary photons cannot penetrate, electromagnetic interactions would be geometrically impossible. Dark matter would curve spacetime in ways that affect our three-dimensional brane gravitationally while remaining physically isolated from our electromagnetic universe. From our perspective, dark matter would appear as invisible gravitational influence, exactly matching observational evidence. Extra-dimensional models make specific predictions about dark matter's cosmic behavior. If dark matter can move freely through extra dimensions, it might not cluster as strongly around galaxies as purely three-dimensional dark matter would. Alternatively, if dark matter is confined to higher dimensional surfaces that intersect our brane at specific points, it could create localized gravitational effects that differ from standard dark matter predictions. Testing these possibilities requires precise measurements of dark matter distribution on various cosmic scales. Mirror matter theories propose an even more radical possibility. Our universe might contain a complete duplicate of ordinary matter with its own mirror electromagnetic, weak and strong forces. This mirror sector would interact with ordinary matter only through gravity and possibly very weak portal interactions that connect the visible and mirror worlds. Mirror matter would have its own mirror photons, mirror electrons, and mirror atoms, creating a parallel electromagnetic universe that remains completely hidden from our observations. In mirror matter models, dark matter consists of mirror atoms, mirror hydrogen, mirror helium, and mirror heavy elements produced by mirror stellar nucleosynthesis. These mirror atoms would interact electromagnetically with mirror photons while remaining invisible to ordinary light. Mirror stars could shine brightly in mirror light while appearing as dark gravitational sources to our telescopes. Entire mirror galaxies might exist in the same cosmic locations as ordinary galaxies, overlapping gravitationally while remaining electromagnetically separate. The theoretical appeal of mirror matter lies in its natural explanation for dark matter's cosmic abundance. If mirror particles have identical masses and interaction strengths to ordinary particles, thermal equilibrium in the early universe would naturally produce equal amounts of ordinary and mirror matter. Slight asymmetries in early cosmic evolution could explain why dark matter slightly outweighs ordinary matter today, creating the 5-to-1 ratio observed in cosmic structure. Asymmetric dark matter models explore another theoretical avenue where dark matter and dark antimatter undergo processes similar to the baryogenesis that created the matter-antimatter asymmetry in our universe. In these scenarios, cosmic evolution preferentially creates dark matter over dark antimatter, while dark antimatter annihilates away, leaving stable dark matter relics. This requires sophisticated dark sector physics involving dark weak forces, dark charge parity violation, and dark electroweak symmetry breaking, essentially duplicating the entire standard model in a hidden sector. The theoretical complexity of asymmetric dark matter models highlights how electromagnetic silence doesn't imply physical simplicity. Dark matter could possess arbitrarily complex internal physics while remaining invisible to electromagnetic observation. Dark matter particles could undergo dark chemical reactions, form dark molecules, exist in dark plasma states, or even support dark biology, all while remaining completely hidden from our electromagnetic universe. Supersymmetric theories provide a more conservative theoretical framework where dark matter emerges from well-motivated extensions of standard model particle physics. Supersymmetry predicts that every known particle has a heavier supersymmetric partner with different quantum properties. The lightest supersymmetric particle, SP, would be stable and weakly interacting ideal properties for dark matter. If the LSP is electrically neutral, it would interact primarily through weak nuclear forces and gravity while remaining electromagnetically invisible. The theoretical elegance of supersymmetric dark matter lies in its connection to other fundamental physics problems. Supersymmetry helps stabilize the Higgs boson mass against quantum corrections, provides candidates for unifying the fundamental forces, and predicts dark matter as a natural consequence. The absence of supersymmetric particles at the Large Hadron Collider has pushed supersymmetric dark matter candidates to higher masses, but they remain theoretically viable if supersymmetry breaking occurs at energy scales beyond current experimental reach. Sterile neutrino dark matter represents a minimalist theoretical approach where dark matter consists of extremely weakly interacting particles, similar to ordinary neutrinos, but without weak force couplings. These hypothetical particles would interact only through gravity and possibly tiny mixing effects with ordinary neutrinos. Sterile neutrinos could have been produced in the early universe through quantum oscillations with ordinary neutrinos, creating a thermal relic abundance that matches dark matter's observed cosmic density. The theoretical challenge with sterile neutrino dark matter lies in producing the correct abundance while avoiding observational constraints. Sterile neutrinos with masses in the keV range could produce detectable X-ray emission through quantum mixing with ordinary neutrinos. Heavier sterile neutrinos might avoid electromagnetic signatures but require non-thermal production mechanisms to achieve the observed dark matter abundance without conflicting with cosmic structure formation. Primordial black hole dark matter sidesteps particle physics entirely by proposing that dark matter consists of black holes formed in the early universe through gravitational collapse of density fluctuations. These primordial black holes would interact only through gravity while remaining completely invisible because their event horizons prevent electromagnetic radiation from escaping. Primordial black holes with masses ranging from asteroids to solar masses could account for dark matter's observed properties without requiring exotic particle physics. The theoretical appeal of primordial black holes lies in their simplicity. They invoke only well-understood general relativity rather than speculative particle physics. However, primordial black hole formation requires specific conditions in the early universe, and observational constraints from gravitational lensing, stellar dynamics, and gamma-ray astronomy limit the masses and abundances that primordial black holes can possess. Quantum field theory in curved spacetime opens additional theoretical possibilities for dark matter's electromagnetic silence. In some models, dark matter particles are geometric excitations of spacetime, itself gravitational solitons or topological defects that carry energy and momentum while remaining electromagnetically neutral by construction. These gravitational dark matter candidates would interact only through spacetime curvature, naturally explaining their electromagnetic invisibility. The theoretical frontier of dark matter physics extends far beyond specific particle models to fundamental questions about the nature of physical reality itself. Why does the universe contain multiple sectors of matter with different interaction properties? How many hidden dimensions or parallel branes might exist beyond our electromagnetic perception? Could consciousness itself be a form of dark matter information processing that occurs through non-electromagnetic interactions? These speculative possibilities highlight how dark matter's electromagnetic silence has opened vast territories for theoretical exploration. While observational astronomy reveals dark matter's gravitational effects with increasing precision, the theoretical landscape for explaining dark matter's fundamental nature continues, expanding into realms that challenge our most basic assumptions about matter, forces, and physical reality. The search for dark matter has become more than a quest to identify cosmic matter's dominant component. It has evolved into humanity's most profound exploration of the hidden architecture underlying physical existence itself. Chapter 10. Cosmic Architecture Dark. Matter's electromagnetic silence has shaped cosmic evolution in ways so profound that without it, our universe would be a fundamentally different place, a realm where galaxies never formed, stars never ignited, and the cosmic story that led to your existence could never have begun. The invisible architecture of dark matter doesn't just provide gravitational scaffolding for visible structures. It creates the cosmic framework that makes complex structure formation possible, while electromagnetic radiation would otherwise wash everything away. In a hypothetical universe composed entirely of ordinary matter, the early cosmos would have remained trapped in electromagnetic equilibrium with radiation far longer than our universe did. Without dark matter's gravitational head start during the radiation-dominated epoch, ordinary matter couldn't have formed the density seeds necessary for later structure formation. Electromagnetic interactions with the cosmic radiation field would have prevented gravitational collapse until much later cosmic epochs, potentially delaying galaxy formation by billions of years. The cosmic microwave background radiation provides a precise snapshot of how dark matter's electromagnetic silence affected early structure formation. The acoustic oscillations visible in CMB temperature fluctuations reveal that ordinary matter experienced pressure waves driven by electromagnetic radiation, creating alternating compression and rarefaction patterns. Meanwhile, dark matter accumulated in gravitational potential wells without electromagnetic resistance, establishing the gravitational framework into which ordinary matter would eventually fall after recombination, freed it from electromagnetic coupling to radiation. Computer simulations of cosmic evolution reveal the intricate dance between electromagnetic and gravitational forces in structure formation. Dark matter-only simulations produce cosmic web patterns that closely match large-scale galaxy surveys, demonstrating how purely gravitational dynamics can create the universe's largest structures. Adding ordinary matter with electromagnetic cooling processes creates the detailed physics of star formation and galactic dynamics within dark matter's gravitational framework. The cosmic web itself, that vast network of dark matter filaments connecting galaxy clusters across hundreds of millions of light-years, owes its existence to dark matter's electromagnetic immunity. If dark matter could radiate electromagnetically, these extended structures would lose energy and collapse gravitationally, creating a universe of dense dark matter concentrations rather than the diffuse gravitational framework we observe. Galaxy formation represents perhaps the most dramatic example of how electromagnetic silence enables cosmic complexity. Dark matter halos provide stable gravitational wells where ordinary matter can accumulate and eventually form stars. Without dark matter's extended gravitational influence, ordinary matter would lack the gravitational framework necessary to overcome its own electromagnetic radiation pressure and collapse into galactic structures. The observational evidence for this cosmic architecture appears throughout astronomical surveys. Gravitational lensing maps reveal dark matter distributions that extend far beyond visible galaxy edges, creating gravitational influence zones much larger than electromagnetic structures. These extended dark matter halos provide the gravitational stability that allows galaxies to rotate coherently for billions of years without flying apart. Dark matter's role in cosmic architecture extends beyond individual galaxies to the formation of galaxy clusters, the largest gravitationally bound structures in the universe. These massive collections of hundreds of thousands of galaxies are held together primarily by dark matter's gravitational influence, with dark matter comprising roughly 85% of cluster mass. The electromagnetic radiation from cluster galaxies represents only a tiny fraction of the gravitational binding energy provided by dark matter. The bullet cluster collision provides spectacular visual evidence of cosmic architecture in action. When two massive galaxy clusters collide at velocities exceeding 4,000 kilometers per second, their ordinary matter components experience electromagnetic drag that slows them down, while dark matter passes through with minimal interaction. Gravitational lensing reveals the dark matter components continuing ahead of the ordinary matter, clearly demonstrating how electromagnetic and gravitational interactions create different cosmic behaviors. This architectural role explains why dark matter's properties are so precisely tuned for cosmic complexity. If dark matter interacted electromagnetically like ordinary matter, it would lose energy through radiation and collapse into dense concentrations, disrupting the extended gravitational scaffolding that supports large-scale structure. If dark matter had stronger self-interactions, it might form overly concentrated halos that prevent normal galaxy formation. The observed properties of dark matter appear optimized for creating stable cosmic architecture. The hierarchical formation of cosmic structure relies fundamentally on dark matter's electromagnetic silence. Small dark matter halos form first through gravitational collapse, then merge to create increasingly massive structures over cosmic time. This bottom-up assembly process requires dark matter to maintain its gravitational influence without electromagnetic energy loss. Electromagnetic cooling would disrupt this hierarchical buildup by allowing dark matter to radiate energy during gravitational encounters. Galaxy rotation curves provide direct observational evidence of dark matter's architectural role in galactic dynamics. The flat rotation curves observed in spiral galaxies require extended dark matter halos that provide gravitational force at large radii where stellar mass becomes negligible. These dark matter halos maintain their extended distributions because they cannot lose energy electromagnetically, creating stable gravitational frameworks that support galactic structure for billions of years. The formation of cosmic structure on different scales reveals how dark matter's electromagnetic silence affects physics across vast ranges of mass and distance. On scales of individual galaxies, dark matter provides gravitational frameworks for stellar dynamics and chemical evolution. On scales of galaxy groups and clusters, dark matter governs the large-scale motions of galaxies themselves. On the largest scales, dark matter creates the cosmic web filaments that define the universe's overall architecture. Weak gravitational lensing surveys map this cosmic architecture by measuring how dark matter's gravitational influence deflects light from distant galaxies. These surveys revealed that dark matter clustering follows predicted patterns from gravitational dynamics while remaining completely invisible to electromagnetic observation. The consistency between gravitational lensing observations and theoretical predictions confirms that cosmic architecture emerges from purely gravitational dark matter physics. The cosmic microwave background's polarization patterns provide additional evidence for dark matter's architectural role in early structure formation. Polarization arises when photons scatter off electrons in regions with density fluctuations, creating characteristic patterns that reveal the gravitational potentials in which ordinary matter fell after recombination. These patterns match theoretical predictions for a universe where dark matter established gravitational frameworks before ordinary matter achieved electromagnetic freedom. Star formation within galaxies demonstrates how electromagnetic and gravitational processes work together within dark matter's cosmic architecture. Dark matter halos provide the gravitational wells where gas can accumulate, but electromagnetic cooling of ordinary matter enables the detailed collapse processes that form individual stars. Without dark matter's gravitational framework, gas would lack the gravitational confinement necessary for efficient star formation. The coevolution of galaxies and their dark matter halos reveals how cosmic architecture shapes visible structure formation over cosmic time. As dark matter halos grow through mergers and accretion, their evolving gravitational potentials affect gas dynamics, star formation rates, and galactic morphology. Feedback from stellar radiation and supernova explosions can redistribute ordinary matter within dark matter halos, but the underlying gravitational architecture provided by dark matter remains stable. Future galaxy surveys will map cosmic architecture with unprecedented precision, revealing how dark matter's gravitational influence extends across the observable universe. Projects like the Vera Rubin Observatory and the Euclid Space Telescope will measure galaxy positions and gravitational lensing effects for billions of cosmic objects, creating detailed maps of dark matter distribution on scales from individual galactic halos to the largest cosmic web filaments. This observational revolution will test our understanding of how electromagnetic silence enables cosmic complexity while potentially revealing new aspects of dark matter's role in cosmic architecture. The precision of future measurements might detect subtle deviations from pure gravitational dynamics that could reveal dark matter, self-interactions, or connections to hidden sector physics. The cosmic architecture created by dark matter's electromagnetic silence represents one of the universe's most profound organizational principles, enabling the complex hierarchical structure that makes galaxies, stars, planets, and ultimately life itself possible within an expanding cosmos. Chapter 11: Observational Mysteries. Despite decades of increasingly sophisticated observations, dark matter continues to present puzzling behaviors that challenge our understanding of its fundamental nature and cosmic role. These observational mysteries arise precisely because of dark matter's electromagnetic Silence. We can only study its gravitational effects indirectly, leaving vast gaps in our knowledge about how dark matter behaves on different scales and in different cosmic environments. Each new astronomical survey reveals unexpected patterns that hint at complex dark matter physics while maintaining the electromagnetic veil that keeps dark matter's true nature hidden. The missing satellite problem represents one of the most persistent observational puzzles. Computer simulations based on cold dark matter models predict that large galaxies like the Milky Way should be surrounded by thousands of small dark matter subhalos, each potentially hosting a dwarf satellite galaxy. Yet observational surveys find only a few dozen satellite galaxies around the Milky Way and Andromeda, suggesting that either most dark matter subhalos remain completely dark or our theoretical understanding of structure formation is fundamentally incomplete. This discrepancy could arise from dark matter physics that goes beyond simple gravitational interactions. If dark matter particles undergo weak self-interactions or couple to dark radiation, small-scale structure formation might be suppressed in ways that reduce satellite abundance. Alternatively, ordinary matter physics, stellar feedback, reionization, or supernova explosions might prevent star formation in most dark matter subhalos, rendering them invisible to optical surveys while leaving their gravitational signatures undetectable. The diversity of galaxy rotation curves presents another observational mystery that electromagnetic silence makes difficult to resolve. While most spiral galaxies display the flat rotation curves that originally revealed dark matter's existence, some galaxies show declining rotation at large radii, others maintain nearly constant speeds, and a few display rising rotation curves that suggest dark matter concentrations increase with radius. This diversity suggests that dark matter distributions vary significantly between galaxies in ways that pure gravitational models struggle to explain. High-resolution simulations predict that dark matter halos should have cuspy central profiles with density increasing steeply toward galactic centers. Yet many observed galaxies show chord profiles with roughly constant central density. This core cusp problem could indicate that dark matter self-interactions transfer energy and reduce central concentrations, or that ordinary matter physics, gas dynamics, stellar feedback, or black hole activity modify dark matter distributions through gravitational interactions. The electromagnetic silence that makes these problems mysterious also complicates their resolution. Unlike stellar populations, which reveal their masses, ages, and compositions through electromagnetic spectroscopy, dark matter distributions can only be inferred through gravitational effects on visible matter. Stellar kinematics, gas dynamics, and gravitational lensing provide indirect probes of dark matter, but these measurements are affected by ordinary matter physics in ways that can mimic or mask dark matter effects. Galaxy cluster collisions offer unique laboratories for studying dark matter behavior during gravitational encounters. Yet these observations raise their own mysteries. While the bullet cluster clearly shows dark matter separation from ordinary matter during collision, other cluster mergers display different behaviors. Some collisions show dark matter and ordinary matter remaining spatially associated. Others reveal multiple dark matter concentrations that don't correspond to obvious collision dynamics, and a few display dark matter distributions that appear offset from all ordinary matter components. These collision observations constrain dark matter self-interaction strength too strong, and dark matter would experience drag forces during collisions like ordinary matter does. Too weak, and dark matter couldn't explain observed separation patterns. Current measurements suggest that dark matter self-interactions, if they exist, must be velocity-dependent or operate only under specific physical conditions. Yet electromagnetic silence prevents direct detection of any interaction mechanisms that might govern dark matter collision physics. Gravitational lensing surveys reveal additional mysteries about dark matter's cosmic distribution. Strong lensing observations of distant galaxies sometimes show lens configurations that require more concentrated dark matter profiles than simulations predict, while weak lensing surveys find dark matter clustering patterns that don't perfectly match theoretical expectations. These discrepancies are subtle and might result from observational systematics, but they could also indicate unknown aspects of dark matter physics. The cosmic microwave background radiation, despite providing our most precise measurements of dark matter abundance, also presents observational puzzles. Recent Planck satellite observations suggest possible tensions between CMB-derived cosmological parameters and values inferred from local astronomical measurements. These tensions could indicate that dark matter properties vary with cosmic epoch, or that dark matter interactions change the expansion history of the universe in subtle ways. Dark matter's role in galaxy formation creates additional observational mysteries when stellar populations are compared with theoretical predictions. The too big to fail problem notes that the most massive dark matter subhalos around the Milky Way should host bright satellite galaxies, yet many remain surprisingly faint or absent entirely. This suggests either that star formation efficiency varies dramatically between similar dark matter halos, or that dark matter halo masses are systematically different from theoretical expectations. The timing and efficiency of cosmic structure formation provide another realm where electromagnetic silence complicates interpretation. High redshift galaxy surveys reveal surprisingly massive and mature galaxies at cosmic epochs when theoretical models predict structure formation should still be in early stages. These observations could indicate that dark matter clustering occurred more rapidly than expected, or that dark matter interactions enhanced early structure formation in ways not captured by current simulations. Stellar stream observations around the Milky Way offer sensitive probes of dark matter substructure that should be detectable through gravitational effects on stellar orbits. Recent surveys have identified several stellar streams with gaps or density variations that could result from encounters with dark matter subhalos. But interpreting these features requires sophisticated modeling of galactic dynamics and stellar evolution. The electromagnetic silence of dark matter makes it impossible to directly confirm whether observed stellar stream perturbations result from dark matter interactions. The distribution of dark matter on cosmic scales reveals patterns that challenge simple gravitational models. Cosmic web filaments show correlations between dark matter density and galaxy properties that suggest complex feedback relationships between ordinary matter and dark matter evolution. Some observations hint that galaxy formation might modify dark matter distributions more significantly than theoretical models predict, creating co-evolution processes that blur the distinction between dark matter physics and ordinary matter astrophysics. Ultra-diffuse galaxies, objects with stellar masses, like dwarf galaxies but sizes comparable to the Milky Way, present particular mysteries for dark matter physics. These galaxies require massive dark matter halos to maintain their extended stellar distributions, yet their formation mechanism remains unclear. Some ultra-diffuse galaxies appear to contain normal dark matter abundances. Others seem dark matter deficient, and a few show kinematic properties that don't match any theoretical predictions. The search for dark matter annihilation or decay signatures in gamma-ray observations has revealed additional mysteries. While no definitive detection of dark matter signals has emerged, several gamma-ray observations show unexpected features that could potentially result from dark matter processes. A gamma-ray excess near the galactic center, unexplained gamma-ray emission from dwarf galaxies, and correlations between gamma-ray signals and dark matter distributions all provide tantalizing hints that electromagnetic silence might occasionally be broken by rare dark matter interactions. These observational mysteries highlight how electromagnetic silence both conceals and reveals aspects of dark matter physics. While we cannot directly observe dark matter particles or their interactions, Their gravitational fingerprints create observable patterns throughout the cosmos. Yet interpreting these patterns requires disentangling dark matter effects from ordinary matter physics, electromagnetic processes, and observational systematics, a challenge that grows more complex as astronomical surveys achieve greater precision and discover new phenomena. The resolution of these mysteries might require fundamentally new approaches that go beyond traditional electromagnetic astronomy to probe dark matter through gravitational waves, neutrino astronomy, or exotic detection techniques that haven't yet been conceived. Understanding dark matter's true nature might demand observational strategies as revolutionary as dark matter's electromagnetic silence is profound. Chapter 12. Future Revelations. The future of dark matter research stretches before us like an uncharted ocean of possibility, where revolutionary technologies and radical theoretical insights might finally pierce the electromagnetic veil that has hidden the universe's dominant component for over 13 billion years. As we stand at the threshold of a new era in cosmic exploration, the tools being developed to study dark matter's hidden realm promise to transform our understanding not just of dark matter itself, but of the fundamental nature of physical reality and our place within a universe far stranger and more complex than we ever imagined. Gravitational wave astronomy represents the most promising frontier for dark matter detection, offering a completely new window into cosmic phenomena that remain electromagnetically invisible. The LIGO and Virgo gravitational wave detectors have already revolutionized astronomy by detecting black hole mergers and neutron star collisions. But future gravitational wave observatories might be sensitive enough to detect dark matter interactions directly. If dark matter consists of primordial black holes, their mergers would create gravitational wave signals with distinctive characteristics. If dark matter undergoes phase transitions or forms exotic objects through self-interactions, these processes might generate detectable spacetime disturbances. The next generation of gravitational wave detectors, including the space-based Laser Interferometer Space Antenna, LISA, and proposed ground-based facilities like the Einstein Telescope, will achieve sensitivity levels that could reveal entirely new classes of cosmic phenomena. These instruments might detect the gravitational waves produced when dark matter structures undergo violent rearrangements, when dark matter particles annihilate in massive quantities, or when hidden dark matter physics creates previously unknown forms of spacetime curvature. Quantum sensing technologies promise to push dark matter detection sensitivity far beyond current experimental limits. Ultra-precise atomic clocks, quantum magnetometers, and gravitational sensors based on quantum superposition might be sensitive enough to detect the minute spacetime distortions that individual dark matter particles create as they pass through laboratory detectors. These quantum devices exploit the fundamental uncertainty principles of quantum mechanics to achieve measurement precision approaching theoretical limits imposed by nature itself. Artificial intelligence and machine learning algorithms are already transforming dark matter research by finding patterns in astronomical data that human analysis might miss. Future AI systems could analyze vast datasets from cosmic surveys, gravitational lensing observations, and particle physics experiments to identify subtle signatures of dark matter interactions. These computational approaches might reveal dark matter effects that manifest only through complex statistical correlations across multiple observational channels. The combination of AI analysis with next-generation astronomical surveys could create unprecedented insights into dark matter's cosmic role. The Vera Rubin Observatory will photograph the entire southern sky every 3 nights for 10 years, creating a time-lapse movie of cosmic evolution that contains billions of galaxies and trillions of stars. Machine learning algorithms analyzing this vast dataset might discover new types of gravitational lensing effects, unusual stellar motions, or cosmic structure patterns that reveal previously unknown aspects of dark matter physics. Space-based astronomical observatories, operating across the electromagnetic spectrum, will continue probing dark matter's influence on cosmic structure formation. The Nancy Grace Rawlings Space Telescope will map dark matter distributions through gravitational lensing with unprecedented precision, potentially revealing whether dark matter interacts with itself or ordinary matter through forces beyond gravity. The James Webb Space Telescope is already discovering massive galaxies at surprisingly early cosmic epochs, providing new constraints on how dark matter influenced structure formation in the early universe. Underground. Dark matter detection experiments are approaching sensitivity levels where they must confront irreducible backgrounds from cosmic rays, radioactive decay, and even neutrino interactions. Future detectors might require revolutionary new approaches. Multi-ton liquid xenon chambers operated miles underground, crystalline detectors cooled to temperatures near absolute zero, or directional detectors that can distinguish dark matter signals from background events by measuring the direction of nuclear recoils. The search for dark matter through particle accelerator experiments continues pushing toward higher energies and more exotic detection strategies. Future colliders might achieve energies sufficient to produce dark matter particles through entirely new interaction mechanisms, while precision measurements of standard model particles could reveal tiny deviations that indicate virtual dark matter interactions. Even null results provide valuable constraints on dark matter properties by ruling out entire classes of theoretical models. Theoretical physics is exploring increasingly radical possibilities for dark matter's nature and cosmic role. Models involving extra dimensions, parallel universes, and exotic space-time geometries suggest that dark matter might be fundamentally different from anything in our current understanding of particle physics. Some theories propose that dark matter exists in a mirror universe that shares our space-time but remains electromagnetically separate, while others suggest that dark matter represents excitations of space-time itself rather than conventional particles. The possibility that dark matter has its own complex physics, dark atoms, dark chemistry, dark biology, opens entirely new frontiers for theoretical exploration. If dark matter can form complex structures through dark electromagnetic or weak interactions, the dark matter around us might support phenomena as rich and varied as ordinary matter chemistry. Dark matter, life might exist in forms so alien to our electromagnetic-based biology that it remains completely undetectable by conventional means. Cosmological observations of the cosmic microwave background, galaxy surveys, and Type Ia supernova continue refining our understanding of dark matter's role in cosmic evolution. Future measurements might achieve precision sufficient to detect tiny deviations from simple dark matter models, revealing whether dark matter interactions change with cosmic epoch, whether dark matter couples to dark energy, or whether dark matter physics involves multiple particle species with different properties. The search for dark matter decay or annihilation signatures spans from radio waves to gamma rays, with each wavelength offering unique sensitivity to different dark matter models. Radio telescopes like the Square Kilometer Array might detect signals from dark matter interactions in the galactic center or dwarf galaxies. Gamma ray observatories could identify the radiation signatures of dark matter annihilation in cosmic ray interactions. Neutrino telescopes might catch the exotic particles produced when dark matter undergoes rare decay processes. Perhaps most intriguingly, the study of dark matter is beginning to converge with other fundamental mysteries in physics and cosmology. Dark matter's electromagnetic silence might be connected to the nature of quantum gravity, the origin of spacetime, or the fundamental question of why the universe contains matter rather than antimatter. Understanding dark matter could provide crucial insights into quantum field theory, general relativity, and the possibility that our universe represents just one phase in a larger cosmic evolutionary process. The philosophical implications of dark matter research extend far beyond particle physics and cosmology. If dark matter truly represents the universe's dominant component, then our electromagnetic universe, everything accessible to light-based astronomy, constitutes only a tiny fraction of physical reality. This electromagnetic minority status might fundamentally limit our ability to understand cosmic evolution, forcing us to accept that the universe's most important processes remain forever hidden from direct observation. Yet dark matter's electromagnetic silence also offers profound opportunities for discovery. Every new detection method, every theoretical breakthrough, and every observational survey brings us closer to understanding how the majority of cosmic matter shapes structure formation while remaining invisible to light. The resolution of dark matter's mystery might require not just new experiments or theories, but entirely new ways of thinking about matter, forces, and the nature of physical reality itself. As we venture deeper into dark matter's hidden realm, we approach what might be the greatest revolution in human understanding since Copernicus revealed that Earth is not the center of the universe. Dark matter's electromagnetic silence suggests that our electromagnetic perspective might be equally provincial, providing access to only a small fraction of cosmic reality, while the vast majority of existence unfolds in electromagnetic darkness beyond our current comprehension. The future revelations awaiting us in dark matter research promise to transform not just our cosmic perspective, but our fundamental understanding of what it means to exist in a universe where the visible represents merely the tip of an invisible iceberg of physical reality. Throughout this journey into the electromagnetic void, we've discovered that dark matter's silence isn't a limitation. It's the key to understanding cosmic architecture itself. We've explored how dark matter's immunity to electromagnetic radiation allows it to maintain the extended gravitational scaffolds that support galaxy formation, while ordinary matter condenses into the electromagnetically active stars and planets we observe. We've examined how quantum field theory explains why some particles couple to electromagnetic fields, while others remain forever mute to light's ancient conversation. And we've glimpsed the theoretical frontiers where dark matter's hidden nature might conceal entire realms of physics operating beyond our electromagnetic perception. Perhaps the most profound insight is that dark matter's electromagnetic silence represents not absence, but presence. The presence of a cosmic majority that shapes everything we see while remaining forever beyond our direct electromagnetic reach. The universe you observe through telescopes, the galaxies whose light has traveled billions of years to reach your eyes, the cosmic microwave background radiation that carries echoes of creation itself, all of this exists within gravitational frameworks created and maintained by matter that chooses to dwell in perpetual darkness. The irony is breathtaking. We live in an electromagnetic universe of incredible richness and complexity, where chemistry creates life, where stellar fusion illuminates galaxies, where the interplay of electric and magnetic fields enables the technology that surrounds you. Yet this electromagnetic cosmos represents less than 5% of physical reality. The remaining 95% consists of dark matter and dark energy cosmic components that interact with our electromagnetic universe primarily through gravity's geometric influence on spacetime itself. This cosmic hierarchy challenges everything we thought we understood about matter, light, and the nature of physical existence. For centuries, humans have explored the universe by collecting electromagnetic radiation light in all its forms from radio waves to gamma rays. We've mapped stellar positions, decoded galactic chemical compositions, measured cosmic distances, and traced the universe's expansion history through electromagnetic astronomy. Yet the majority of cosmic matter remains completely invisible to these electromagnetic investigations. Dark matter's electromagnetic silence suggests that our cosmic perspective might be fundamentally limited by our electromagnetic biology and technology. We evolved to sense visible light, We've extended our perception across the electromagnetic spectrum, and we've built a scientific understanding of the cosmos based entirely on electromagnetic communication between distant objects and Earth-based observers. But what if this electromagnetic window shows us only a tiny fraction of cosmic reality? Consider how this electromagnetic limitation shapes scientific knowledge itself. Every astronomical discovery, from the moons of Jupiter to the acceleration of cosmic expansion, has emerged from electromagnetic observation. Every laboratory experiment detecting subatomic particles relies ultimately on electromagnetic interactions to create observable signals. Even gravitational wave detectors use electromagnetic laser interferometry to measure spacetime distortions. The scientific method itself appears constrained by our electromagnetic tools and electromagnetic intuitions. Yet dark matter's gravitational fingerprints prove that electromagnetic invisibility doesn't mean cosmic irrelevance. Through gravitational lensing, galactic dynamics, cosmic structure formation, and precision cosmology, we've learned dark matter outweighs ordinary matter by more than 5 to 1. The invisible universe isn't separate from the visible universe. It's the gravitational foundation upon which visible structures exist. Every galaxy, every star, every planet owes its existence to dark matter's silent architectural influence. This gravitational connection between electromagnetic and non-electromagnetic reality hints at deeper principles governing cosmic evolution. While electromagnetic interactions create the complex chemistry that enables life and technology, gravitational interactions provide the cosmic frameworks within which electromagnetic complexity can flourish. Dark matter's electromagnetic silence allows it to maintain the extended gravitational scaffolds that support galactic evolution, stellar formation, and planetary system development. The search for dark matter has become humanity's most profound exploration of hidden reality. Underground laboratories, buried miles beneath the Earth, shield sensitive detectors from electromagnetic contamination, while hoping to catch rare interactions between dark matter particles and atomic nuclei. Particle accelerators smash protons at near light-speed energies while searching for missing energy that might signal dark matter production. Space-based observatories map gravitational lensing patterns that reveal dark matter's cosmic distribution with increasing precision. Yet each experimental advance also reveals the extraordinary challenge of studying matter that refuses to participate in electromagnetic communication. Dark matter detection requires us to develop entirely new experimental approaches. Gravitational sensors sensitive to individual particle interactions, quantum devices that exploit uncertainty principles to achieve ultimate measurement precision, artificial intelligence algorithms that find patterns in cosmic data too complex for human analysis. The theoretical implications extend far beyond dark matter itself to fundamental questions about the nature of physical reality. Why does the universe contain multiple sectors of matter with radically different interaction properties? How many hidden dimensions or parallel realms might exist beyond our electromagnetic perception? Could consciousness itself represent a form of non-electromagnetic information processing that remains as hidden from our scientific instruments as dark matter particles? These questions highlight how dark matter research has evolved from cosmic accounting, determining how much matter exists in the universe, to ontological exploration of reality's fundamental architecture. Understanding why the majority of cosmic matter remains electromagnetically silent might require revolutionary insights into quantum gravity, space-time geometry, and the possibility that our four-dimensional electromagnetic universe represents just one aspect of a far more complex cosmic reality. As you contemplate the hidden cosmos surrounding you, remember that dark matter isn't distant or exotic. It's intimately present in your immediate environment. Dark matter particles are streaming through your body at hundreds of kilometers per second, passing through every atom without leaving electromagnetic traces. The gravitational field of dark matter in our galactic neighborhood influences the motion of our solar system through space. The cosmic web of dark matter filaments provides the gravitational architecture that connects our local galaxy group to the largest structures in the observable universe. The story of dark matter's electromagnetic silence ultimately reveals that the universe is far stranger, far more complex, and far more mysterious than our electromagnetic intuitions suggest. We inhabit a cosmic reality where the majority of matter chooses to remain forever hidden from the most versatile force we know, where gravitational architecture shapes electromagnetic complexity, where the visible universe emerges from invisible foundations. This cosmic perspective transforms how we understand our place in existence itself. We are not observers of a primarily electromagnetic universe with minor gravitational influences. We are electromagnetic beings living within vast gravitational architectures created by matter we cannot see, surrounded by particles we cannot touch, embedded in cosmic structures whose true nature remains hidden beyond our electromagnetic horizon. The future of dark matter research promises to push these boundaries even further, using gravitational wave astronomy, quantum sensing, and artificial intelligence to probe deeper into the hidden realm that shapes our cosmic home. Each new discovery brings us closer to understanding how electromagnetic and gravitational reality interweave to create the cosmic tapestry within which stars shine, planets form, and consciousness emerges to contemplate its own invisible foundations. Dark matter's electromagnetic silence isn't the end of cosmic mystery. It's the beginning of our recognition that the universe contains far more than our electromagnetic senses can perceive, far more than our electromagnetic science can directly study, far more than our electromagnetic imagination has yet conceived. In learning why dark matter doesn't emit light, we discover that light itself illuminates only the smallest fraction of cosmic reality, while the vast majority of existence unfolds in electromagnetic darkness, shaping everything we see while remaining forever beyond the reach of photons to reveal. If you made it this far, subscribe and give a thumbs up. Check out my video on why gravity is actually the strongest force in the universe. I'm sure you'll love exploring how the weakest force becomes the most influential on cosmic scales. The invisible universe awaits your curiosity, and there are so many more hidden realms to discover together. In the beginning, we asked why the universe's most abundant matter refuses to emit light. Now we know. Dark matter's electromagnetic silence isn't a failure to communicate. It's the cosmic principle that makes our electromagnetic universe possible.